All right, let's get right into it. We trust software with pretty much everything, but lurking deep inside the code are these tiny, often invisible errors. You could call them ghosts in the machine, and they can cause some absolutely catastrophic failures. So in this explainer, we're going to go on a bit of a ghost hunt to uncover 3 of the most fundamental flaws in software.
It sounds completely impossible, doesn't it? I mean, it's like breaking the basic laws of math. But in the digital world, this exact paradox isn't just possible, it's a security nightmare that attackers have used to break into some of the most protected systems on the planet.
You know, every single line of code is an instruction, a tiny gear in this massive digital machine we've built. But even the most brilliant engineers make mistakes. And these aren't just your typical bugs that make an app crash. Nope, these are more like hidden doorways, just waiting for an attacker to find them. Today, we're going to see exactly how these doors get left wide open. So our first ghost is one that messes with the most basic thing a computer does, counting. Let's take a look at what happens when simple math goes horribly, horribly wrong.
Okay, so the core idea here is that computers don't have infinite space. They have to store numbers in fixed-size containers. Just imagine trying to pour a gallon of water into a tiny pint glass. It's going to overflow, right? Well, in computing, when a number gets too big for its container, something really, really strange happens.
This is the perfect analogy. The number doesn't just hit a wall and stop. Instead, it flips, or wraps around, all the way back to its smallest possible value, which is often 0. And it's this sudden, totally unexpected wraparound that creates a massive security hole. And here's where it gets really clever and dangerous. Attackers know this can happen, so they can carefully craft an input, say by trying to order an impossibly large number of items, just to trick the software. They trigger that wraparound on purpose, making the program think a huge number is actually a tiny one, and that leads the program to make a critical mistake.
Let's look at a real bit of code to see this in action. On the left, the vulnerable code adds 2 numbers together first, and then it checks if the result is too big. But what if that sum overflows? It becomes a small number, and the check passes by mistake. The secure code on the right is much smarter. It checks if the numbers are about to cause an overflow before it even does the addition. A tiny change in logic that makes all the difference.
And believe me, this isn't just some theoretical problem. Remember the GDI plus vulnerability? This was a massive security flaw, and at its heart was a simple integer overflow. It affected pretty much every Microsoft user because a specially crafted image file, just a picture, could trick the software's math and trigger the overflow.
From a user's perspective, the attack was devastatingly simple. You just open an email or visit a web page, and a hidden malicious JPEG image would exploit this flaw. And the result? Well, you can see it was catastrophic. The attacker could gain complete and total control of your computer. That one tiny math error literally handed them the keys to the kingdom.
All right, on to our next ghost. This one doesn't break math. It actually tricks the program's own language. It manipulates the special codes a program uses to format and print text, and that can lead to some seriously dangerous outcomes.
The key phrase to focus on here is user-provided input. In programming, functions like printf use special codes, like %s for a string or %x for a number, to format text. The vulnerability happens when a programmer is careless and lets a user's input become the instructions for that function.
This is such a great analogy. Think about it. The program is like a news anchor just reading a script from a teleprompter. If an attacker can write on that script, they can make the anchor say anything. By sneaking in codes like %x, they're basically telling the program, hey, forget what you were supposed to print. Instead, read a secret from your memory and show it to me. It's a direct line into the program's brain.
And the classic example of this is the woofftp bug. This was a really popular server program, and this one tiny mistake, passing user input straight to a printing function, allowed attackers from anywhere in the world to take over entire servers with just a few carefully crafted characters. It was a really harsh lesson in how dangerous misusing a single function can be.
And you know it's just wild? How simple the fix is. I mean, look at this. The vulnerable code on the left just prints the user's input directly, no questions asked. The secure code on the right explicitly tells the function, hey, treat this input as a plain string of text, and nothing more. That's it. That one tiny change, just adding %s, completely slams the door shut on the attacker.
Our final ghost for today is all about timing. It's not about bad math, it's not about tricky language, it's about what happens when 2 digital actions happen in an order the programmer just didn't expect. This is truly a race against the machine.
Right, so the thing to remember is that modern computers are doing millions of things all at once. A race condition happens when the final outcome depends entirely on which of those things finishes first. If the program isn't carefully designed to handle this chaos, things can go very, very wrong. The parking spot analogy is just perfect for this. So a program checks something, like, is this file safe to open? And it gets a yes. But in the split microsecond between that check and the moment it actually opens the file, an attacker can swap it with a malicious one. The program thinks it's opening the safe file, but it's too late. It lost the race.
And one of the most famous, or maybe infamous, race conditions of all time has got to be dirty cow. This was a flaw deep in the Linux kernel. That's the core part of the operating system that controls everything. This made it incredibly dangerous. It was a really subtle timing bug that had been hiding in plain sight for years, and it was unbelievably powerful.
So here's how it worked. An attacker could trigger a very specific race condition that would trick the kernel into letting them write to a file that was supposed to be read-only. This completely shatters one of the most fundamental security rules. By winning this tiny race, a normal everyday user could effectively become the all-powerful root user and take over the entire machine.
So we've met the ghosts, right? Bad math, tricked language, and broken timing. So how in the world do we fight them? Let's pivot now from the problems to the solutions and see how developers are building more secure software today.
The three flaws we've talked about, integer overflows, format string bugs, and race conditions, are all part of a larger family of what we call memory-related errors. You can see them on this chart, along with another big one, buffer overflows. They all basically stem from the computer not handling its own memory in a perfectly safe way, which creates these opportunities for attack.
The good news is, we know how to defend against these ghosts. It really comes down to discipline and using the right tools for the job. Choosing modern, safer languages can eliminate entire classes of these bugs right from the start. Enabling special compiler protections can automatically warn you about potential integer overflows before you're even done writing the code. And of course, conducting thorough code audits can help you find those really sneaky, hard-to-spot race conditions. These are the pillars of building a real digital fortress.
So, we've only just explored 3 of these hidden ghosts. It really makes you think, doesn't it? The software we all depend on is built on layers and layers of complex code, and a single tiny mistake can unravel the whole thing. It really begs the question, what other invisible flaws are out there that we're relying on every single day, just waiting for the right conditions to show up?